Yeah, thank you, Mr. Chairman. Excuse me for the inconvenience. Our presentation was previously scheduled for another session, but due to some reasons, it was removed to this session. And it is regarding metallic materials. It's a collaborative work between our research center. I'm from research center in Herion in Hamburg, close to Hamburg in Geesthacht, a small city. And the colleagues are from University of the Aegean in Greece. In principle, the main work was performed within this PhD thesis of Theano, EXAMILIOTI, and my colleagues Benjamin KLUSEMANN, another colleague from the Greece, Christina, Margarita, Charalampidou, and Nikolaos Alexopoulos is also from Greece. Okay, what is the motivation for the work? We are dealing with laser welding, and the idea is to apply laser beam welding to join aeronautical structures in airframe. And the first idea is to use efficient manufacturing process instead of riveting, what is very time consuming. Another idea is to realize lightweight structures with laser beam welding. We do not need the overlapped area, and therefore we can reduce the weight of the structure. And here is the typical implementation of the riveted connections in airframe. And here is, for example, photo how the welded structure can look like. Okay, another motivation is to use, instead of state-of-the-art alloys, which will find applications such as 2024 material, for example, as a skin, and 7075 as a stringer material, to use innovative materials with further lightweight and improved mechanical properties such as aluminium lithium alloy. And here is for example, composition of the new developed of the third generation aluminium lithium alloy 2198. We can further reduce the weight and increase, for example, modulus of elasticity and mechanical performance. And some background for aluminium alloys. Aluminium alloys are precipitation hardened alloys, and we can increase or adjust the properties by an appropriate heat treatment, and precipitates can influence the dislocation movements, and therefore we can have adjusted stress-strain behavior of the material. Here is mechanisms, and the idea is for precipitation hardened alloys, we need to optimize the heat treatment. We have a conquering situation between the temperature and time to achieve it. In the first stage, we have improvement of mechanical properties up to the peak aging condition, and afterwards we have decrease. So far, we have to find a good balance for the heat treatment. And the idea was, this is, for example, how the properties of the base material look like for different heat treatment conditions. We have peak aging, for example, achieving after 48 hours the maximum strength, the yield strength that can be achieved. After that, we will have overaging, and it can be achieved by different combination of time and temperature. And the idea was to find an optimal process parameters for welding of this alloy using laser beam welding, and optimum parameters for the post-weld heat treatment to find a good balance with regard to mechanical properties of the weld. And we investigated welding for the material 2198 with two thicknesses, 3.2 and 5 millimeter in thickness. And during welding, we also investigated the effect of different wires. The typical wire is high silicon content alloy 4047. And in our work, we also considered wire with a kappa as a base alloying element. And we performed optimization with regard to welding, and we investigated different heat treatment conditions after welding. Okay, here is the overview. And for characterization, we used tensile specimens extracted from the welded sheet in the middle, and we performed tensile heat treatment and tensile testing. For heat treatment, we used the typical furnace, and heat treatment was performed for different time, between 3 hours and 98 hours. Okay, and mechanical testing. We performed tensile testing using the electromechanic testing machine. For example, this was in our laboratory from Zwick. And here are their results. With regard to micro hardness, if we deal with precipitation hardened alloys, we will have always decrease of hardness because we introduce additional heat input during welding. And therefore, this is the question of further optimization with regard to post-weld heat treatment, how we can improve the behavior. Is it possible to increase a little bit hardness after welding? And we see here are the results for 40, if we use high silicon content filler wire. It's we do not have here enough flexibility, but in case of kappa with a kappa content 2319, we can a little bit increase hardness in the fusion zone if we apply heat treatment for 48 hours. And we also investigated the effect of post-weld heat treatment on the mechanical properties. We see if we have, as welded condition, we have reduced level of yield strength. And if we apply post-weld heat treatment, we can somehow increase the yield strength and mechanical performance of the joint. And we investigated this for 2 conditions. And also the Professor Alexopoulos proposed the method for characterization of mechanical performance of the welded joints by means of the quality index. The quality index, it is the energy required to introduce the deformation into the specimens up to the failure of the specimen. And the higher the energy is, the higher the quality of the welded joints. And here the welded joints were also evaluated with regard to their quality and index to find a good criteria for assessment of the welded joints. And you see that the joints with 2319 filler wire show lower quality for all the investigated conditions compared to the joint welded with a high silicon content wire 4047, because we have higher ductility in the joint. Okay, and here is the results, and we investigated in both conditions, welded with regard to material of 5 millimeter thickness and 3.2 millimeter thickness. And here are the conclusions of our work. Addition of silicon, if we use 4047 filler wire, enables higher hardness in the fusion zone in the as welded condition than the copper-based, for example, wire 2319. Both investigated filler materials exhibit almost the same response to artificial aging condition, where yield stress in peak aging conditions shows slightly lower for the wire 2319 when compared with wire 4047. elongation at fracture was inversely decreased with post-weld heat treatment up to 98 hours, and overaging condition, investigated thicknesses. Both thicknesses present similar behavior with higher yield stress to be observed for 5.0 thickness, and for all artificial aging condition. And the concept of quality index was exploited to characterize and to assess, to quantify mechanical performance of the welds. And the concept of quality index was shown that the joint specimens with the thickness of 5 millimeter always have a high quality index than the respective specimens with 3.2 millimeter thickness. The highest the quality index was achieved for the peak edge conditions. Yeah, thank you very much for your attention.